Theorem 7.3, arc length of a parametric curve. Now it's really kind of interesting where this formula comes from. This says, consider the plane curve defined by the parametric equation. So x equals xt and y equals yt. And we're going from t1 to t2. And then it says, and assume that xt and yt are differentiable functions of t. Then the arc length of the curve is given by this formula. So the cool thing about this formula is it's really intuitive where it actually comes from. So if I draw this curve here, and let's say this is my endpoint, this is my next one over. The idea here is I can create these triangles. And now think about this thing here. That's going to be close to that curve, maybe not exactly the curve. But let's realize what this is here. That's my change in x. This here is my change in y. So the idea then is, how can I find out that hypotenuse? It's going to be the square root of the change in x squared plus the change in x, or change in y squared. And that's what that formula turns out to actually be here. That's how I find that hypotenuse. And if I keep doing all of these triangles, I will systematically get all of those triangles that way. So really what I end up with here, this is my change in y, and this is my change in x. So I really get this formula. Now this would only be for one of them, but remember what an integral does. An integral is saying, hey, I'm going to take n of them, and that's where this dt comes from. And the integral is actually a limit as that gets very small. So these are actually getting smaller. These triangles are getting smaller and smaller as I keep going. So it's breaking these t's into smaller and smaller pieces. And that's what an integral does, and it shrinks it down to 0. So we get an exact value though. So it's really kind of cool where this formula does come from. So now what we're going to do is we're just going to use this formula now and just do an arc length and just figure out the value of it. So here's our problem. So let's take a look at this one. It says find the length of the curve. X equals e to the t minus t. Y equals 4e to the t over 2 from -8 to 3. So essentially what we're going to do is this simply means here that we got to take the derivatives of x and t with respect, x and y with respect to t. Okay, so that means we're really going to need x prime t. And x prime t is going to be e to the t minus 1. And then y prime t is going to be 4e to the t over 2, because e to the t is equal to e to the t, times 1/2. So then when we clean this up a little, this will actually be 2e to the t over 2. And that's going to be my y prime t. So now I have both pieces here, and now that's what, so my x prime t is really this piece here, and my y prime t is really this piece here. So I'm just going to sub that in there and use this handy dandy formula. Here we go. So we're looking at our s equaling the integral from -8 to 3, because we had our bounds here. Okay, and that's going to be square root of, and then I'm going to put this in there, e to the t minus 1 squared plus 2e to the t over 2 squared, and all square rooted dt. Now again, this is going to give us our arc length, as we're finding the length of the curve. So then simplifies to this here. Now one thing to remember here is that when I have this, this e to the t minus 1 squared, that's really e to the t minus 1 times e to the t minus 1, and I actually have to FOIL that out. So I'm going to get more than just e to the 2t minus or plus 1. So be careful with that. It's actually a FOIL there. So anyways, I end up with this here. And keep in mind here, this ET squared is really e to the 2t. So I just put that in place of it. Now I'm just going to do this integral. In most cases, these integrals are going to be done by hand because the most part, they really never really work out well. This one actually does, but not very many will. So this really is just, if I factored it, e to the t plus 1 squared dt. Now, if you didn't catch that, always look for those kind of things too. And what tells me that this is like an x squared, this is like a 2x, and that's like a plus 1. That's what I was looking at when I seen that. So anyways, it factors nicely. And the reason why this one, why you want to factor this one is because those are going to cancel out. So now I end up with not 0 to 8, negative 8 to 3. And this is really going to be e to the t plus 1 dt. And this is actually going to be a very simple integral to integrate now, since we're able to simplify it as much as we did. So the integral of e to the t is e to the t. And then 1 is going to be plus t. And that's going to be from negative 8 to 3. So this one's going to be e to the 3 plus 3 minus, and that's going to be e to the negative 8 minus 8. So then our final answer is going to be, so there's our answer. That's the arc length.